So vector products, um, here's essentially two vectors written in Euler form of a complex number. It's going to work here. Okay. So one of the keys here, there it is. We can write vectors essentially as polar form of complex numbers, and then we can multiply them. So, okay, quick review. Oh, no, okay, I'll show you how to do this. Okay, we can do that. So we're going to say this is the vector 2, 3. Mhm. So 2 plus 3i. So 2, it's as a 2 plus 3i. Here, I'll just show it because it might be needed in the future. And then we have to get this angle in here, get the hypotenuse. It's the right triangle. 2, 3, square root of 13 using Pythagorean theorem. And angle is going to be inverse tangent of 3 over 2. One of the important things with the angle is that you have to place it in the correct quadrant. $56.3. The square root of 13, CIS, 56.3 degrees. Usually Euler form would be done in radians. So on the calculator it does. Converting that to radians. Point 982. No, 0.983. So Euler form would then be hmm, it just is. Yes, radians is a unitless measure. It's kind of like because it's a distance on the unit circle, I think. If I'm doing conversions, I'll write RAD. And then it kind of goes away. So we could add them with those for 2 dimensions. That works kind of well, but not for 3. Or we can multiply, convert it to Euler. We're not going to actually do it that way. Sinusoids, same kind. The multiplying is easier. Yeah, I I wouldn't add them in Euler form. I would add them in standard form. Yeah, a little bit. Um, yeah, I would just add them as standard. I would just 5 minus 4i. Uh, and yeah. We're going to do a lot of multiplying not in complex number form, but that is an alternative method. Sometimes it's easier. If it feels like they're polar, like the one that was on that test, yeah, if it feels like they're going in circles, I would probably use polar form of complex numbers. That's like Zappy on the test, in the Unit 2 test. Yeah, that's those are the questions that getting them right. Well, you have to get some other stuff right, but the ability to get those right is kind of the getting seven type of thing. And if you can get some of it, you still might be able to get a seven. Like that's a those are really those are really advanced concepts. So mhm, yeah. So points in space can be defined using vectors. Vectors can show interactions in space. If an object is acted on by an electric, magnetic, or gravitational field, then vectors can be used to predict the effect of an object at a point in space. These forces may speed up or slow down a moving object depending on the direction in which they act. The strength of the interaction will also depend on the magnitude of the forces, which are also vectors. Scalar multiplication represents directional multiplication. For example, it can show the combined effect of two forces. If two forces are at right angles, how they will interact. If they act in exactly the same direction, how would they calculate the total effect? And what would you do if neither perpendicular or parallel? The vector product can be used to find the area of a parallelogram whose sides are two vectors in a plane. In three dimensions, it can also be used with the scalar product to find the area of a parallelepiped, which is a six-sided solid whose faces are parallelograms. The vector product of two three-dimensional vectors represents the vector that is perpendicular to both of these vectors. It is possible to generalize the vector product of n-dimensional vectors, and so what would this represent? It finds the vector product. I will explain. I'll explain through a few examples when we get there. The vector product is going to be next Tuesday. And it's going to be Tuesday, not Monday, because of a different lesson I have to give Monday. Oh no, I have to be in a meeting Monday. That's what it is. But yeah, I did not want that one to be a video. You have a video on Monday. I will start 314 graph theory. It the beginning of graph theory is really easy. Okay. Theory of knowledge, the scalar products, sine, cosine are often used to discover unknown knowledge. When you think about it, it's pretty amazing that you can use mathematics to create unknown knowledge that's also valid. Consider other areas of knowledge. Do they operate in a similar way? Can you identify any other areas of knowledge that are self-perpetuating in regard to knowledge construction in the same way math is? Any Could a historian use history to create new knowledge? Art probably does. Okay, yeah. And like I think art has more. I'm not sure about history. Natural sciences use a lot of math, so oh, that's kind of cool. Uh-huh. That is kind of cool. So, scalar product. Scalar product, also known as the dot product. So I'm going to give you and you've done dot products. in pre-calc. Scale, they're the same thing. And the cross product, we do actually use an X for multiply.
So are both student products?
No,
They're different.
the cross product is the vector product. The dot product is the scalar product. And it's represented with vector v dot w or vector v x w. They are two different products. This is why we have lessons. They are two different vector products. Dot has a dot and cross. This is, yeah. This is why these are the shortcut names. I'll probably try to use them interchangeably so you're used to both. Because I guarantee you, I guarantee you that this they're going to use scalar and vector product in questions if they sometimes they just won't tell you which product and you'll have to figure it out. But I guarantee you that that's what they call them on the formula sheet. And that's what they will call them in some IB questions. And I guarantee you, you will have professors that call it the dot product and cross product at some point. And you might have professors that call them the scalar product and vector product. So you just need to know that they're both. I'm more familiar with them as dot product and cross product. Although I don't know where I learned the cross product. I'm not sure I really did. I'm not sure I was really taught it. It's I'll show you how to develop the formula on Wednesday. You're not gonna have to do it, but yeah, I'll under if you can understand why it is, that will help you understand what's you don't have to memorize it. It's in the formula packet. Yes, yeah, it helps you. If you understand the why, you know when to use it better, and that makes a lot of things. So the dot product is essentially multiply the x's, multiply the y's, multiply the z's, add them all. 2 times cosine of the angle. Sometimes. What's really wonderful about this is this you can use this to get the angle between vectors. So if you have vector equations for lines, you can get the angle between any two lines by doing the dot product, probably this way, equal to the other way, and then you can get the angle. It's a great little trick. I wish that somebody had taught me vectors like this when I was in high school. Yeah. Two. Okay. Finding the scalar product. So one times two plus -1 times -1 plus 0 times 2. 3! The scalar product is 3. They call it the scalar product because it gives you a scalar. The cross product, on the other hand, gives you a vector. That's why it's called the vector product. That kind of makes sense.
Yeah.
Like, oh yeah, these names actually the scalar product gives you a scalar, or the aka the dot product. The answer is a scalar. When we do the cross product, the answer will be a vector. Ooh. Okay, that's 6 minus 2 minus 4. That one equals 0. And there's a special property about this. Now, vectors are orthogonal. You know what the word orthogonal means? Mm-hmm. It's perpendicular in 3D space. Uh, I was like, you remembered that product wasn't hard. That's going to be an important property for various AB problems. Okay. Let you get that copied down. When the dot product is 0. So these are perpendicular. What's the value of A? Well, we do the dot product. It says these vectors are perpendicular. It should say orthogonal. Mm-hmm. A plus 2 equals 0. A is negative 2. And so I said they would give you the angle between vectors. Usually you take the dot product the other way and then divide by the magnitudes, and that gets you the cosine. And we did do that in pre-calc.
3D.
They're perpendicular within some plane. You just don't know what the plane isn't necessarily flat. It's just, cut through space. It makes, yes, two lines always make a plane if they intersect.
Is that right?
For orthogonal, I don't know the y on that. I was like, yeah, I don't know the y on that. I didn't do enough vector classes. You would potentially prove stuff like this in linear algebra, maybe. Find the exact value of the cosine of the angle between these two vectors. Okay. So it asked me for the cosine. Mm-hmm. Mm-hmm. It didn't ask me for the angle, it just said for the cosine of the angle. So, mm-hmm. The magnitude on this one is square root of 3. So the dot product equals 1 plus -1 plus 2. That's 2. That's my cosine. I believe that's correct. What? Wait. What? They rationalized and reduced?
They don't. It's not normal.
I know.
Sometimes they do, sometimes they do. On comedy, though, they do ask, but in person, it's weird. On comedy,
Yeah. So reducing the radical, I'd pull out a 3. I'd pull out a 9. 6 over 18 is square root of 2 over 3. I believe I'm right there. Yeah. So square root, the cosine of theta is the square root of 2 over 3. A lot of times you'd want the angle, so you'd use inverse cosine. But they asked me for the cosine. So you do have to be careful on these to read the question and answer what the question asks, not what you assume it asks. Because I was about to, inverse cosine that. Give you theta. Didn't ask me for theta, it asked me for cosine of theta. So consider these vectors, use scalar products to show they are parallel. So property that they're parallel. Two vectors are perpendicular if and only if their scalar product is 0. What is parallel? Well, let's find their scalar product and see what. Oh, the angle. Okay. I bet you we'll find that the angle between them is undefined, meaning it doesn't exist. Or actually, maybe the angle between them is 0. That's what we would find. So V dot W equals 3 plus 12 plus 27, 42. Root of 1 plus 4 plus 9. I'm in the magnitudes. 9 plus 36 plus 81. I kind of think that this is going to be 1, since it gave me this hint. That's 1. Okay, cosine of theta equals 1. Theta equals 0. So the angle between my two vectors is 0. That means they're parallel. Because knowing vectors have no location, parallel vectors are just the same direction. So now we're going to find the angle between these and it wants it in degrees to 3 sig figs. So it's specific. So A dot B equals -2 minus 3 plus 6. Oh, that's 1. Square root of 1, 9, 4, that's 14. Square root of 4, 1, 9 is also 14. So the cosine of theta equals 1 over square root of 14 times square root of 14, or cosine of theta equals 1 over 14. Inverse cosine of 1 over 14. $85.9. This isn't so bad, is it? Don't worry, they find interesting applications for these. So now we're going to do the angle between two lines, which is one interesting application. They'll find some others. So remember that our lines in vector form are
The angle between two vectors. Wouldn't there be two angles? Like right here, there's an acute and obtuse angle. So
yeah, it's going to give you the I think it's always going to give you the acute one. Uh-huh. So, well, I think what we're going to do is we're going to actually find the angle between the two vectors. So if the vectors are this way and it's that, it'll give you the angle between the direction vectors. So when we're talking about vector equations for lines, we have the initial position, and then this is the direction vector. So that's which way it's going. So what we're actually doing is we're finding the angle between the direction vectors. So if the direction vector's angle is obtuse, it'll give you the obtuse angle.
Yeah. So, but here, L1, L2, like, aren't those like all right direction vectors?
Those are the two direction vectors. That's the B and the D. And they're intersecting. So the angle between the lines, yes, you have an obtuse one here, but the angle between the direction vectors is acute, so it'll give you an acute. If the angle between the direction vectors were obtuse, yes, you'd get an obtuse. So thinking about it just as the direction vectors, not as whole lines. That's how you'll get the angle. Mm-hmm. Mm-hmm. So angle between two lines. So they've got what on earth are they doing here? I don't know. Let's find the angle between these lines. So I'm going to double check that I'm not doing anything this, but we're going to take the two direction vectors and we're going to find the angle between those. So we need the 149, that's 50, 59. We need the magnitudes. Six. I'm gonna call them B and D. Just for notation purposes. I suppose you could write this as 1, 7, -3 dot -9, 6, -15 halves.
So we're only the direction.
The direction vectors. The, the point. Yep. Because I'm trying to find the angle between them. The angle is based entirely on direction. Uh-huh. Yep. And so the dot product is -9 plus 42 plus 22.5. 55.5. To make sure I got that right. Yes. That's interesting that they did that. They're very into fractions on this one, apparently, instead of using decimals. Uh-huh. It might be 55.5 over this just seems way easier to do with decimals. And I'm just going to do the inverse cosine of that right away.
Mm.
56.7. Now I'm going to go back and read the question and make sure I answered it in the, it did not ask for it in any particular form. So 56.7. It didn't, it says in degrees to one decimal place. It did not specify what it wanted. I wanted to double check that it didn't ask for radians. Usually this would make more sense in degrees with vectors, but okay, find the acute angle between these two lines. Okay, well, we might have to, it might give us an obtuse, I don't know. So -1, 4, 1, -2 equals -1 -8 equals -9. Square root of 17. It did ask you for the acute, yes. Do 180 minus. Mhm. Yes. Yes, and it does give you an obtuse angle. 167.471. So I just do 180 minus that. 12.5 degrees. It does say this one says in degrees correct to one decimal place. So notice that they did a nice job. They did not round until the final answer. They kept more decimal places than they needed until the final answer. It probably doesn't matter at that point, but it's a good habit. Okay, find the angle between these lines. Okay,
It's giving us one correct.
it's given it to us in the other form. How lovely.
Wait, let me just.
And so, all we need to convert. Let's grab our IB formula packet because it's there. And this isn't as hard as it looks way worse than it is. I know that. So, parametric form. I think this is going to be 1/4 to 0 plus lambda 1/4 -1, 1. That's what I think. Let's see if I'm right. L4, L1 is parallel to the vector 4, -1, 1. 4, huh? Yeah, I'm confused from the formula packet here. There's
Wait.
So I did this. So I put it into that form. Oh, and I probably want to get it into the other side. So I'd multiply it. So this x0, y0, z0. So I'm multiplying by 4. That's where I get the 4 here. Oh, wait, I know what they do. Sorry, I got it. I figured. Now this will work. So they're all set equal to lambda. So 4 lambda equals x plus 1 minus 1 plus 4 lambda equals x. So I'm
Oh,
trying to get -1 plus lambda 4. when I do lambda equals 2 minus y, lambda minus 2 equals negative y equals lambda plus 2. Oh, yep. So negative 1. And then lambda equals z, so that's just 1. And this is a 0. So my direction vector is 4, negative 1, 1. So back to this. L1, really, we just need the direction vector for negative 1, 1. L2,
Three plus.
hmm, 1. I think it's negative 1. I'm going to write it out. Since I already made a mistake once, let's write it out. Yes, it is. Yes, it is.
Point.
0. Yep. We don't necessarily need it, but that's good information to be able to know. So find the angle between the lines. Okay, let's get the magnitudes. Put it, yep, or square root of 18, square root of 11, L1 dot L2 is, I guess it's not really L1 dot L2, it's 12 minus 1 plus 1. Okay, 12. So now I'm going to go over here and do cosine theta equals 12 over square root of 18. When I multiply square roots, they can be in 1. I found the dot product down here. Yes.
No.
Oh, the magnitudes. Inverse cosine. Yeah, I found them right. I just write them right underneath. And instead of doing square root of 18 times square root of 11, they just multiply the insides. So theta equals 31.5 degrees. It doesn't specify 3 sig figs.
Well,
It doesn't specify, so the default 1 decimal. This one didn't specify. Wait a second. 44.7. What did they get for a dot product? 12
oh, we can use 3
square root of I have a negative 1 here. Oh, I didn't use it there. It's 10. Okay. That's I couldn't read my negative 1 when I did my dot product. Hmm. That's a minus 1, so this is 10. $44.7. There we go. So that's using the scalar product. It's not radically difficult, but they will throw little tricks in to go, do you remember this and that? And Yeah, the trick on the last one was put it all together. And then by the IB exam, they'll ask you to apply it with calculus. And no piece of it is all that hard. It's just putting all the pieces together. Okay, so that's 13.1 and 13.2.